The next thing that we're going to need to do is to start putting all the pieces together. So I have this document that I've created called the curve sketching algorithm, which is just kind of a guideline to follow so that we don't forget anything along the way. After, I'll go through an example with you guys, kind of step by step of how to follow this algorithm, but it's kind of up to us what order to do things in, and then I will go through in future videos other examples where I'm still going to be using the algorithm, but I may kind of group some of these things together to be a little bit more efficient. This right now is just kind of like a checklist, a process that we could use, but it's kind of up to us. As long as everything gets covered is really what's important here. So we'll look at it real quick. This says first thing that we would look at is the domain and x and y intercepts along the way. We want to look at the domain so that we know if there's anything that's restricted, because later on when we get critical numbers and possible points of inflection, we have to be aware of whether those could actually be points or not, or whether they were already restricted at the beginning. Then we would look at all asymptotes and behaviors around them. We could look at our vertical asymptotes and horizontal asymptotes, and this would also correspond to obliques, because we analyze horizontals similar to how we analyze obliques. Then we would get into actually taking derivatives. So get the derivative, find critical numbers, use it to find intervals of increase and decrease. That'll help us sketch it, which also then tells us, number 5, to determine local extrema. And we can do that either through that first derivative test by the chart we would have created here, or we could use a second derivative test by looking at concavity, which we would do here. To determine points of inflection in concavity, get the second derivative, and we would find points of inflection by finding the second derivative's kind of critical numbers, and then charting those things out as well. And then when we compile all this information, we should be able to sketch this curve. Okay, so let's try an example. Let's do this very first one. We're just going to start with kind of a simple polynomial. So here we're going to sketch this thing out. Okay, just some degree 3. In terms of its domain, because it's polynomial, we're not restricted at all. It's going to go through every x value in the real number system. X-intercepts, the way that it's written right now, we can factor this thing using just common factoring and then some trinomial factoring here to find where its x-intercepts are going to be. Find the y-intercept, plug in x being 0, so it's going to happen at 0. Then next in our algorithm would be to look at asymptotes. This one doesn't have any, it's polynomial, so we can skip that over that part. Number 3, we would then get into finding critical numbers. So I'm going to take the derivative, I'm going to set it equal to 0, and then to find the critical numbers, I'm looking for where the derivative is 0 or where the derivative itself is undefined. In this case, the derivative is defined everywhere, so we're just looking for zeros, so factor this thing as much as we possibly can, or get zeros another way. In this case, we've got a couple of critical numbers showing up. Okay, 5/9 and -1. Then, what we'd need to do is to try and chart this out so we could see intervals of increase and decrease if I'm following this curve sketching algorithm, which I'm going to do for this example. In terms of the factors that's there, I've got a -1 from there, and then I've got these other ones put in here. My critical numbers are breaking up my domain in order from -infinity up through to positive infinity. And then I've populated my chart, and I've summarized this at the bottom. So my first derivative looks like it is changing signs from negative to positive back to negative, which means that right here it is my function f is decreasing, then it is increasing, then it is decreasing. So from that I got all my increasing and decreasing intervals, and then from this I could also conclude my local extrema. So here I've got local min going down here because this was decreasing to increasing, and then here it was increasing to decreasing, so I should have a local max. And then we can get the y coordinates just by taking those x values and plugging them back in here to get the full coordinate. In order to find the concavity and points of inflection, take the second derivative, set it equal to 0, and then find its so-called critical numbers from here. We'll just call these possible points of inflection. So zeros, or anywhere where it is undefined, it's only got zeros. So we've got only one possible point of inflection. And then I can chart this out the same way we did prior to the break. And then here it looks like we've got a concavity change. This is going from concave up to concave down. So at -2/9, we have a point of inflection. Get the y-coordinate from plugging it into the original function. And we've got our intervals for concavity. And then we would just compile all this information together. So this is what my function would look like. I'm going to show you how the information would get compiled. First thing I would do is start plotting in all the key points. So from our information we had x-intercepts, so I'm going to put those in. We had local max and a local min, so I put those in. And we also found a point of inflection, so I would put that in and label the points. These need to be put on the graph. They're the key points on the graph. Then we could go through and follow with increasing and decreasing intervals. I know my function was decreasing and then increasing and then decreasing, and I can combine that with my concavity because my function was concave up until here and concave down for the rest of the time. So putting the concavity together with the increasing and decreasing, you have the full shape of the graph. Okay, which should hopefully makes sense from what you guys remember from advanced functions, because this was degree 3 with a negative leading coefficient, so quadrant 2 to quadrant 4. And all of its zeros were of order 1.